topic that we covered since it's a very early stage into the semester and we haven't covered many things. I was thinking, can we do something like a dense reconstruction of, for example, Rome, whatever things? That's probably a bit more difficult and never get into that. So we're thinking about something about lenses and camera models, which you guys already know about. I think last lecture, the professor talked about the linear least square solution of camera calibration. Is that the thing that he talked about? Okay, I think everyone is nodding, which is good. Because today, we're gonna bump it up. We're gonna put a bit more spice in it. It's gonna be a bit more difficult. And how difficult it is, we'll see right after I start the presentation. But key thing I want to mention beforehand is, although this is certainly not going to be included in the midterm, it do help you understand the least square and the corresponding, or like linear least square, non-linear least square, camera model, and typically how do you calibrate the camera model. All right. So let's get started. All right. So first thing I want to talk about was, So first thing I want to talk about was previously we mentioned, you guys, when do all those lenses have the thin lens assumption, they're thinking, oh, this lens is acted perfectly, which in reality would have never been the case. The lens has distortion, lens has thickness, and this thickness introduced spherical aberration, which when you see this is here, it's perfectly focused. The aberration light is focused on one point, but this is what actually happened. Well, it's exaggerated, but you can see it. So everybody can see it. They're not, the light supposedly focus on one point. They're not really focusing on one point. And if you have an image plane slicing here, this point will be focused, and you will get that ring-like image of even if you have a point as a light source. So this is called spherical aberration. If you think about how the thickness of the lens act in the equation, it actually increases the effective distance where the light travels. So the thicker the lens, the longer the distance actually the light travels. Although when you look at this, they all travel the same distance, but the effective distance of light travel is larger here and shorter here. Right? So that's the way of extremely simplified how the spherical aberration works. So, Professor were talking, there was a very cool study that derived a closed form analytical solution on how do you design a single lens. So usually, how you correct this, you can design a group of lenses and to correct this spherical aberration. So not a single lens anymore. And then so there was a 2018-2019 study that designed the lens in a very particular way so that it doesn't really have this spherical aberration. The equation is very simple, and I think everybody would understand. I will upload it in the Carmen, and if you got a chance, you can take a look. But I will just put the equation here so that you guys can take a look. And yeah, so obviously I'm not going to cover this, which not trying to embarrass myself. So what are we actually going to cover today? By the way, if I finish early, you guys, we'll just, you guys can leave early. So I will just try to finish as soon as possible so you guys can have a nice dinner tonight. Not too late, go back home like 9 p.m. So today we're going to talk about something called omnidirectional camera. I think Alish mentioned it sometime earlier in the lecture. He was saying, those complicated things. So today we're going to talk about this. We're going to talk about what is the camera model for this, what would be the image of it look like, and how do we calibrate it if time permitted. So there are three types of omnidirectional cameras. Dioptric camera, which is like kind of like the fish eye thing, right? It's you typically get from your cameras. Not typically, but it's kind of have that extremely distorted version. It's around 180 degrees field of view. And then you have something called Catadioptric camera, which is the kind of the thing that Alish mentioned. It has a very interesting design, which on the top, when you see here, this is actually a mirror, right? This is a mirror as like a parabola or parabolic. How do you call this thing? Paraboloid? 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 Is that how do you call it? Okay, paraboloid. So, thank you. All right. Or like when you slice it, it will look like parabolic curve. So it's a curved mirror. So it's like this thing that if you do cycle, biking or jogging, then you have that U-turn thing. And at the tip of the U-turn, you usually see those mirror. They're extremely curved that you can actually see your side and the other side. So this is kind of, you put it vertically and see it this way. And my eye now is kind of like the camera, CCD, the image plane. And I see in this way, right? So the camera is here. And see this way and receive the light reflected from this mirror. And what is the good thing about it? It's a continuous mirror, so you can see everything in this range without a problem. You don't have to go with this. We'll talk about this very soon. And it's just a solution with one camera and a particularly designed mirror. So, and then we have this. Pretty much when everybody talk about omnidirectional camera today, is kind of talking about this. It's kind of like a cluster bomb, which it has multiple camera in this kind of spherical structure. The good thing about this is it can actually see almost 360 degree, meaning like it's entire spherical field of view. Other than you might want to support, other one you'll just throw it. So then this thing usually works is kind of like a multi-view geometry thing that you guys will learn very soon after, later in the class, that you'll do the epipolar geometry and you might do image stitching and put everything together nicely and it will be that. But it's nothing, because we haven't covered most of the thing in this camera, so I'm not going to cover this. So today I'm going to cover this. So some of my curious, like, what does the image look like? All right. So that will be the image look like, right? The image, so the camera showed it this way. This will be the surrounding. You see the little walls, a car here. So it's a 360 degree in this kind of field of view, not like on the top, right? You can see this thing here. So that's just an intuitive visualization of what the camera would see. If you imagine yourself as a camera, and you look ahead, and that's what you see. All right. Okay. So then the question is, why do we care? Why do I even want this thing? Right? It looks extremely distorted. It looks like it doesn't even look like some of the building doesn't preserve the linear structure anymore. It's extremely distorted. So for us, human, our visual system, we have two eyes. We have a field of view which is, a little bit smaller than 180 degrees. So when we want to see the other side, we have to turn, right? Just like the cameras. For the camera, when you turn, a lot of parameter changes, right? So at least it might rotate a little bit. The translation, of course, is going to change. So, and then if you want to have a structure to get the omnidirectional photo using one single camera that's just regular camera, then you have to have a mechanical structure for it. Then you have to turn, right? This one prevents that. But on the other hand, what is it like? What could this one be used for, right? Usually when we, find the path, like I know if I want to go out, I'll go this way. But if there's somebody behind me trying to shoot me, I wouldn't know. So this one gives a much wider sensoring range in it, just like those fascinating whatever thing in Naruto that you can see whatever in 360 degree. It's widely used in robots because the robots don't want to turn so much to see whatever behind. So when we use this, then the first thing we want to know is, what is a camera model? What will be the object? If I have an object, it's like, obviously those have a rectangular shape. And now it becomes this kind of like a curved structure. What will be the image look like if I have something like a point in a 3D dimensional space? So that can be answered by the camera model of this specific camera. All right. So then we'll go to the fun part. So I'm going to derive the camera model by hand. Not very complicated, but it does have a few steps. So, okay, the thing is already there. Let me grab a pen. Can everybody see it? Can you see it? Yeah? Okay. Yeah, good. All right. So this will be the paraboloid. Is that right? Paraboloid? Paraboloid is the 3D thing, right? So this is the paraboloid of that mirror. It's a mirror with a paraboloid shape. And so here, the coordinate system goes with z, this very traditional x, y. And the image plane is here, right? Somewhere underneath, right? Not presented here, but somewhere underneath. So let's say we have a point here. Let's say it's P X, Y, XP, YP, ZP. All right, so the X, Y, Z coordinate of the point P is XP, YP, and ZP. So how does this kind of imaging things, how do we find out, how do we trace the light? How does the light behave in this kind of system? Because we know the lens, it kind of, if you shoot it a parallel line, if it's an ideal line, it will converge. Ideal lens will converge at the focal point. So for this kind of mirror system, what we really care is one ray of light shooting to the mirror, but pass through the focus. That's the thing we care. Why? Like, why do I only care about this? Because similar to regular lens, the light that shoots through this mirror and reflect will be perpendicular to the image plane and parallel to the optical axis. So what we have is this. We have a light that's going straight down to the image plane. So this light will be directly received by the camera. So then people are still going to ask, like, yeah, sure, but why not something like a little bit deviate from that? So if you have, that's the simplification assumption we have to introduce, where we don't care about the light rays that are deviate from the perpendicular direction to the image plane. Why? We can put the image plane really far away, and those lines that deviate a little bit from the perpendicular position will go out of the sensor. Does that make sense? Make sense? Yeah? Right? Somebody asking questions? No? Okay. So that's the only thing that we care. And only light rays that we care. So then what would be the map, what would be the projection of this point onto this mirror? That would be the intersection of this light ray with this paraboloid structure. If we find the closed form solution for this, we know what P would be located at on this mirror. So let's do that right now. Anybody remember how do we represent paraboloid? Yeah? Okay. See somebody, I think somebody remember this. So this paraboloid has a specific location. Its focus is located at the origin of the world coordinate system, right? So to represent this, let's call it S. So like, let me just change to the one that was more ink in it. So S will be Z equal to 1 over 4 for x squared plus y squared minus f. F, what is F? F is the focal length from the vertex of the paraboloid to the focus of the paraboloid. All right, minus F because the vertex is in the negative range of the z-axis. And then let's denote this as O, the origin. What would be the parametric formulation for this line? The line will be OP, this OP, x over xp to right, that will be the line equation. All right, that's better. All right, and so now we have this. The only thing we want to do is just to find the intersection of the two. So how do we do this? Let's first say this point is P prime. Right, P prime has U, V, and let's say, it doesn't really matter, but let's put it as Z prime. So let's focus on U first. U, which corresponding to the X in the original parabola equation. So let's go with replacing Z with an expression of X, replacing Y with also an expression of X. All right, combining this and this, we got this. That is an expression with respect to X. All right, that's when we want to find what would be the U like. So to solve this, XP will be, because this equation that I have to change this to XP, right? Because that's the point, that's the line that we're interested in. Oh, I don't think that's the case. Okay, let me think about it. Oh, no. Okay, yeah. Right, because so here it's still x squared from here. Y is equal to yp over xp times x, and plug it in here, and that will be the equation. And then let's do. And then we can combine this term into right, 1 plus xp squared, 1 plus xp squared over yp squared times x squared. It just pull it out, put it outside the parentheses, and you get this. And let's see. And then what we want to find a solution for this. And then everybody probably already know this formula, which have a quadratic form, has a specific closed form solution. That if you rearrange this thing, right? So that will be the function we want to evaluate where's the root at, and that will give us the u coordinate, right? To solve this, we know if we have something like a times x squared plus b times x plus c equal to 0, what will be the solution? The solution will be something like anybody know? Okay, so it will be 2a on the denominator, and it will be b plus minus square root of okay, good. All right. So you do this. You do exactly what you guys said, right? Plug it in. What do you have? Is u equal to all right, is that right? That will be the solution. Is nobody following me? Somebody nodding? All right. So this minus canceled, 4 canceled, f canceled. All right, so what is equal to? Right, equal to this. And when you combine, so you can, now you can add this, right, merge this two, plus this, and then become the only one. So here, in the denominator, you got zp squared plus xp squared plus yp squared. Right, this. Let us say this is equal to r squared. So then you can rewrite this. Rewrite this entire equation, entire expression to so u will be then equal to this, zp over xp plus minus r over xp. So then, both sides you have xp, and you have plus minus here, right? And then you have 2f. And now what you can do, you can get rid of this, because both sides has this xp squared with this. So let's denote this as zp plus minus r over 1 over 2f xp squared plus yp squared over xp, right? The x canceled out at the numerator and denominator. So notice that xp squared and yp squared, what is it equal to? It equal to, right, r squared minus zp squared. Very good, very good. So let me just flip it upstairs, like upstairs to the denominator. So it's r squared so then this and this can cancel to the extent where you can have the denominator has as r minus plus zp, because r squared minus z squared is equal to r plus zp times r minus zp, right? And whatever here it is, you get one term to cancel out. Make sense? Okay. So with all this, I mean, not really complicated, but a few steps, you get u equal to, let's see, qfx r minus plus zp. All right, that's what you get for u. And you can do the same thing for v, which is corresponding to y. And the good thing about this specific formulation is x and y are exactly symmetrical. So you can just say, similar way, you will get, it's a lazy way to say things, y r minus plus zp. So that will be the projection of a 3D point onto the mirror that has the paraboloid shape. Right? That's the x and y. That's u and v. We haven't talked about z yet. We haven't talked about z yet, but we don't care. Why we don't care? And so first, does everybody follow on this equation? Yeah, kind of, not really. Okay. Oh, you mean this here?
Yeah.
Let me see. Yes, that's right. We have an XP here. Yep, that's the one. Right, good, everybody? Good, all right. So now we have u, and now we have v here, and we have z prime. So why I said I don't really care about z prime? Because at the end of this point, we'll project onto image plane. So because we're only focusing on the light rays that are passing through the focus, and every ray will be perpendicular to the optical axis and perpendicular to the image plane. So here, if we get the image plane, every light passing through will be perpendicular to that. So you guys learned camera models, right? We got weekly perspective, all of those camera models. If you have light rays that always coming parallel to the optical axis, what would be the best camera model to use? I think Alish covered this. All right, orthographic projection. Where orthographic projection simply drop the z coordinate. Is it, you know what? I don't care about z because they are so far away that it doesn't really matter. So here is the same thing. Because of this nice property that our simplified assumption introduced, we don't really have to care about z. So when you project onto the image plane, this thing becomes the coordinate here with respect to the world coordinate, right? U prime, V prime. That will exactly, U prime, V prime, that will equal to U and V in the world coordinate. But in the image plane, you might have skewness, you might have aspect ratio, the coordinate, the origin doesn't line up, so you always have all of those parameters, intrinsic parameters to estimate. And we'll talk about this. So if I write down, including all of the skewness, aspect ratio, the entire formula will be so alpha is aspect ratio, and beta is skewness, and the psi x is the mirror, the center of the mirror, projected onto the image plane, and this is the y coordinate of that center, right? So everybody, does this looking familiar to everybody? Right, and then you replace this with the coordinate we just derived, the expression we just derived, and you will get a mapping from the 3D coordinate to the image plane for the for this type of camera system. Yes. That's a very good question. You remember when we say what we really care about the projection on the mirror, what we're trying to find, we're finding the intersection of the light OP with this paraboloid. How many intersections there are going to be? 2. Here and here. But one of them, we don't care. Right? So, this will be something that you guys will think. The thing that we care is this. See, raise the plus 1. Why is that the case? That will be you guys' food for thought maybe later this week. All right. So does this derivation make sense to everybody? Yeah? No? Yeah? Go.
Negative minus 1 in the equation.
Negative minus 1.
Just minus 1.
Which part?
I think that u should be equal to minus 2f.
Which should be equal to minus 2f?
The u.
Oh, this, you mean there is a minus here? You say this should be minus, and this should be minus. Why is that the case? Because you have, let me see. Are you saying here? I don't think that's the case. you might be right on this, but I don't think that's the case. If you have your derivation, we can talk after class about this derivation. I think it should be right on this. All right. Okay. So everybody's okay with this. All right. So you have so what will be the intrinsic parameters? What will be the parameters you want to estimate for this camera model to calibrate it? You want to estimate this f, the focal length. You want to estimate alpha, the aspect ratio, the beta, the skewness, and also the mirror center, psi x and psi y. And what will be the easiest way to calibrate it? You just get a bunch of points in the world coordinate. You say, this is a bunch of point x, y, z in there. And then you measure the corresponding point in the u prime and v prime. It's plugged in, and you say, this equation should hold. So what I do is I put the minus here. And use nonlinear least square to solve it. One way of doing this. Because of the difficulties of this expression, it's actually pretty difficult to solve. So what we can take, so to calibrate this, instead of using this kind of brute force method, we can take advantage of the nice property of this mirror, which a specific object, when you check its image onto the image plane, it has another very specific shape. So if I have a line in the world coordinate, in the world, that we want to find the image on, what would be the image of that line using this camera system? What will be the projection of the line onto the image plane? Think about it, what we have in the intuitive, the photo that I show you guys. If I have a line that is infinitely long, it will be a what? So a circle. Very good, very good. Is that a educated guess? Is that like an intuitive kind of answer? That's very nice. It will be a circle. So how do we kind of make sense of it? If I have a line in the world coordinate, right? The only thing that we care, remember, is the light that emitted from that line that passing through the focus. We can construct a surface that includes both this line and the focus. And this surface will intersect with this paraboloid. So what will be the intersection be? It will be an ellipsoid. Not an ellipsoid will be a 3D thing. And then we'll project it onto this, that will be a circle. But we'll prove it analytically. All right. Everybody have this already? Can I erase this? Okay. Yeah, we'll just leave this one here. Do you have questions? No? Okay. All right, so what we want to do, we have a line. Let's say we have a line here. And what we want is we want to construct a surface that includes both this line and the focal point. What will be the representation of it? Let's go with, so at least to mention what will be the hyperplane representation, right? What will be the hyperplane representation? Anybody remember? Usually requires two components. You get so if you have a hyperplane, you have a normal and you have a offset, right? The bias. So here, luckily, the bias is 0 because it's passing through the focus, where the focus is at the origin. So the plane will be represented, let's say, as nx, x, plus ny, y, plus nz, z equal to 0. And right? This is the representation, is the parameterization of the hyperplane, where the bias is 0, and the normal will be parameterized by nx, ny, and nz. Because it's a normal vector, we just normalize it to have a magnitude norm 1. So then the question is very similar to what we had last time when we project a point onto this mirror surface. What now we want to do is we want to find the intersection of this surface with this paraboloid mirror. So how do we do this? We do it by, so z is equal to this, and we just have this entire thing, plug it in, and see what happens. All right, that will be the expression after you plug it in. And then what we do, we multiply 4f over nz. It's kind of like the mathematical massage of the equation. And you multiply 4f over nz on both sides. So what you have is you have 4f nx nz x plus all right, so then this with this cancel out, and this becomes 4f squared. Right? Make sense? No? See, most of the people are already lost, I think. All right. So I'll go through this anyways, and I may put the derivation online so that you guys can check out after the class. Right? And so this equation, we can reformulate it because this has a quadratic form with respect to x, and it has a quadratic form with respect to x. But the question is then, is the quadratic form give us a circle, or is it give us something else? So what we can do, x squared, just rearrange the entire equation. Right? So this should be more like familiar with you guys. You can actually change this to a very specific form that is right? So we can rearrange it as x plus this squared, y plus this squared plus something, right? Something that we want to plug it in so that the equation holds, equal to 4 squared here. So what will be that something? That will be the square of this term and square of this term and minus. Right? So let's do Oops. All right, square is equal to this. Anybody following me on this? Just rearrange it, artificially make this and this hold, and we have to add and subtract a term, right? We add this term here so that this specific squared quadratic form can hold, and then we have to subtract it here, right? So then what we do, we move this thing to this side, all right? So let's see. Right, so now here it becomes 4y squared plus a 4y squared plus a 4y. If you just drag everything else, it will be 1 plus this plus this. So what would this be? Is there any specific property of this nx between this nx, ny, and nz? Is there any specific property of it? Remember what it is? It's the normal. Exactly. So what we had is this. We use this, replace it here. What we get? We get a f4 squared for this, right? And then if you change it to, if you put a square out, that will be a 2f over nz squared. Look at this. Look at this. What is it? A circle. A circle which center at x equal to minus 2f nx over nz. Y equal to center of the circle, the y coordinate of the center of the circle is equal to minus 2f ny over nz with a radius of 2f over nz. So this, remember, what is this? Is the x and y coordinate of this intersection. And luckily, we're using orthographic projection, right? The z, we don't care. We actually only care about x and y. After you project it onto the image plane, it is actually a circle, right? Which is corresponding to what you said. So it means every line segment, when projected onto the image plane through this camera system, will be an arc of some circle. Every line. So if you find lines in the world structure, in the world that you're imaging on, and then you will find that line becomes an arc of some circle, right? That will be the key for us to have a closed form calibration of the system. But there is more than this. There's more to this kind of thing. This specific circle, this circle that is on the image plane, also have a dedicated property that if you find, now it's a circle, but if I expand it to a sphere with equator same as this circle, you will find this sphere always passing one point, a fixed point. What is that point? Now we're deriving that. Okay, let's see what we have. All right, so let us construct a auxiliary sphere with equator like this, right? Equator as the thing that we just derived. So the parametric formulation of that sphere, let's say it is cx minus x squared plus cy minus y squared plus z equal to r squared. Where r squared will be this. Cx, cy will be minus this and minus this respectively. So this is the parametric formulation of the auxiliary sphere. So what will we do? Let's try setting x and y to 0. This is equal to 0 and that equal to 0. Remember, what is cx? Cx is the negative of this, right? Now we squared it. So it will be all right. This will be after you setting x. This will be the formula, and we want to see what will be the z is. What will be the z is? If you move this thing to this side, what would you get? You get 4f squared nz squared 1 minus nx squared minus ny squared. What is 1 minus nx squared and minus ny squared? That's the nz squared. So this entire term canceled out. It means the z, oh, this is z squared, sorry. No, somebody's picking it up. Z squared, this is z squared. So z squared always equal to 4f squared. So it means it doesn't matter where the line is. If we construct a auxiliary sphere in the image plane from the arc that corresponding to the line in the world, it's gonna pass 0, 0, plus minus 2f, right? This z squared, so that z is equal to plus minus 2f. It always passes this, regardless of where the line is. It can't be inside the lens, of course, but outside the lens, it doesn't matter where it is. It always passing that. And what is the good thing about this? Notice what is actually you get from this. You get one of the parameters out of this. F is actually what you're looking for. So what can you do? What can you do on this to get f? You get 3 lines. When it projected onto the image plane, you got 3 arcs. For each of those arcs, construct the auxiliary sphere. Their intersection is 0, 0, plus 2f. And once you get the coordinate of their intersection, that will be, and checking the z coordinate, that will be your 2 times your focal length, right? So remember, when we're deriving this, they're all in the world coordinate, right? And then you still have to consider the cosine x and cosine y for the translation of the mirror center. Make sense? So that's the good thing about this calibration process. To estimate f, you don't actually need to know the 3D coordinate of the lens. What you only need to know is they are collinear. It doesn't matter what is the coordinate. As long as they're collinear, construct an arc find the sphere, find the intersection, and you're done with F. And all the others will follow using nonlinear least squares. Is there any, when is the class end?
You got 5 minutes.
5 minutes. That's everything I'm going to cover today. You guys got 5 more minutes for your dinner. All right. And this is not going to be covered in the midterm. Let me just emphasize it again.